Yeah, so today we're going to be talking about spectroscopy of several Apollo soil samples, particularly focusing on the agglutinate portion of the soil. Before we dive in, I just want to quickly give a shout out to all the folks listed up here. Although I'm presenting this work today, this couldn't have been done with all the folks here, so thank you to all of them. All right, so to get started, in case you're unfamiliar, agglutinates are these particles found in the lunar soil. They're a product of space weathering processes, and they're these fused agglomerates of mineral and glass and iron. Now, in heavily weathered soils or mature soils, they can be more than half of the soil content. In this talk, we're going to be specifically focusing on the spectral properties of agglutinates, specifically the visible to near-infrared reflectance. And we care so much about this because by knowing more about the spectral signature of the agglutinate portion of the soil, we can better interpret spectra of the bulk soil and perhaps better derive composition. Now, even though these spectral properties are so important, the current state of knowledge is actually fairly limited. Most of our understanding comes from this work by Peters et al. 1993. And what they did was they painstakingly separated out these agglutinate particles from a soil by hand and gathered their reflectance spectra. Now, these data were obviously very difficult to get with the manual separation, and they've been very valuable for helping us understand the spectral role of agglutinates. Yet there is a bit of a limitation here. These spectra are all from a single lunar soil, 10084. So it's a little unclear how well these spectra generalize to representing agglutinates across the surface of the moon. So we still have this lingering question. What are the spectral properties of agglutinates across the surface of the moon as it varies in composition and maturity? So to address this question, we extended the work of Peters et al. By separating out agglutinates from 6 different lunar soils, as shown here. We selected 4 of these soils to represent a range of compositions, and we selected 3 of them to represent a range of maturities. And for each of these soils, we gathered reflectance spectra from the 125 to 250 micron size fraction, which we chose because it was the smallest size fraction where we could still efficiently manually separate out the agglutinates. So as an example of some of these spectra that we've gathered, here are the spectra for soil 62231, which is a mature highland soil. As you can see, for each soil, we have 3 different kinds of spectra. We have the dotted line showing agglutinates, dashed line non-agglutinates, and black line, solid black line unsorted, which is essentially agglutinates plus non-agglutinates. Now, we immediately see some clear differences among these spectra. The agglutinates are lower in reflectance, which matches their visually darker appearance. And there's a difference in the spectral slope, which is most clearly seen if we switch over to a plot of normalized reflectance, where it's very clear that the agglutinates are much steeper or redder in slope than the unsorted and non-agglutinates. All right, so now that we've kind of oriented ourselves with the kinds of spectra we'll be looking at, let's see how these spectra vary for soils of different maturities. Here we're showing spectra for the submature and mature soil samples. And as before, the agglutinates are shown by the dotted lines. And I'd like to contrast these spectra with the spectra for the immature soil shown in blue. We see that the immature soil spectra have higher reflectance and have stronger absorption bands. But despite these differences between the immature and the other soils, if we look at the normalized reflectance, we actually see that for the 3 agglutinate spectra, they actually have fairly similar slopes. Like there are some differences, but they're well separated from the unsorted and the non-agglutinate spectra. All right, moving on to spectra for soils of different composition and looking at normalized reflectance. Here we have the non-Mare soil, the low titanium Mare soil, and the high titanium Mare soil. And we see again that the agglutinates have this very steep, much redder slope, while in this case, the non-agglutinates are all shallower in slope than the unsorted soil. And this picture gets a bit more complicated when we add in the highland soil in black, but we're still seeing that the agglutinates have this much steeper slope. And this is interesting because it suggests that for the size fraction, the agglutinates are playing a dominant role in reddening the unsorted soil spectrum. And this result is interesting because we typically think of reddening of a soil happening more because of the small nanophase iron grains in the rims of soil grains, both non-agglutinates and agglutinates. And meanwhile, we think of agglutinates as having these larger nanophase iron particles within them that contribute more to darkening of the unsorted soil. So these results, the very red slope for the agglutinates, got us thinking about the nanophase iron within these agglutinates. Could we say something about them based on this agglutinate spectral data that we have? And for that, we've been comparing our agglutinate spectra to spectra of nanophase iron in silica gel from the work of Noble et al. So here what we're seeing is the agglutinate spectra as the solid colored lines and the nanophase iron spectra as the dashed and dotted lines. In this case, all the nanophase iron spectra are for nanophase iron of average size about 40 nanometers, and the 3 different spectra are for different weight percent abundances. So for this plot, we see that there isn't really a good match at all. The spectral slopes are very different between the nanophase iron and the agglutinates. But if we look at spectra for smaller nanophase iron particles, so on the left 15 nanometers, on the right 35 nanometers, here we're starting to get a better fit. A caveat here is that this is very dependent on the abundance as well. Like for example, on the right side, neither the 0.02 weight percent or 0.2 weight percent are really good matches, but one might imagine that some intermediate abundance could be a good fit for our agglutinate spectra. So in summary, we've gathered these agglutinate spectra, non-agglutinates, and unsorted soil for this 125 to 250 micron size fraction, and they'll be available from the Brown University Relab database if you'd like to use them. And from these first observations, we've seen that the agglutinates appear to contribute to reddening of the unsorted spectra, at least at this size fraction of 125 to 250 microns. And in comparing the agglutinates to nanophase iron spectra, it seems that the best match is for an nanophase iron of about 15 to 35 nanometers or so, and with sufficient abundance as well. And I will leave things there with a slide of all our spectra. And I guess we're doing questions after, right?
No, so yeah, we've got a couple of minutes there for questions. If there's any, I don't see any
questions
in the chat, but yeah, anything in the room. Paul, you can take those.
Sorry. Yeah, thank you. We do have time for 1 or 2 questions in the room. As a reminder, there's a microphone in the middle of the room. And I would ask anyone that is interested to just come up and ask the questions.
Hi, Deborah Lemang for Planetary Science Institute. Apologize for walking in a little late. Can you say something about the range of sizes of the nanophase iron that you think are in agglutinates?
In the agglutinates, yeah. So based on these matches, we might expect maybe like 15 to 35 nanometers. But I do want to point out that for these spectra, it could also be that there's mixing, right? Like it could be smaller nanophase iron and large nanophase iron mixing to produce the slopes that we're seeing. I think, I'm not sure about the data for these specific soils, but I think a lot of the nanophase iron is like 4 to 30 nanometers or so in size. And I think it gets bigger for the interior nanophase iron within the agglutinates.
Thank you.
Yeah.
And just quickly, we had a question in the chat from Michael Poston, which was wondering, are the sorted samples available for sharing?
The sorted samples, we do still, we're still working on them, so we'd prefer not to share them yet until we're done working on them. But I suppose, I'm not sure what the protocol is for that with the Johnson Space Center, but
sure, I guess something to probably think about then as you.
Yeah.
Great.
We'll take maybe one quick question from the room.
Okay.
Yeah, hi, Dave Blewett, Johns Hopkins APL. Sort of picking up on the last 2 questions, maybe what Deborah was getting at is, do you have any plans to, do SEM work or something on your samples to actually see what the size distribution of the nanophase iron is in your samples?
Yeah, so we have taken some SEM images. We haven't analyzed them quite yet. But yeah, that is something that would definitely add to this a lot. Yeah, thanks.